Welcome back to module 1 of the course time dependent quantum chemistry. We have so far introduced time dependent Schrodinger equation, and then we have to some extent discussed or given an idea the meaning of quantum particle and classical particle. So, with that idea we will move forward. We will move on to the solution of TDSE, and we will find out the solution of TDSE, time dependent Schrodinger equation, assuming that for a single particle we are considering. So, we have particle of mass m and single particle, and we will assume that the wave function, total wave function, again I point out that rigorous meaning of wave function and density and its meaning in terms of experimental observable will be discussed very soon in this module and also later in this course. So far it may appear little mathematical, but we will try to understand the meaning behind it. So, the total wave function psi xt, we will assume that when we are solving time dependent Schrodinger equation, we will assume that we can express this total wave function as a product of the space and time part. We can separate it and we can express in terms of this product. So, that is our first assumption to find out the solution. Second assumption we will make, which we have already pointed out, that H, that Hamiltonian operator, does not explicitly depend on time. That is also another assumption we will make to solve this TDSE. So, what we will do, if it can be used in the product form, I will be able to insert this product form to this equation, and let me start. If I insert it, then what I get is that psi x equals the product form I have inserted. Now, we know that this is time independent, Hamiltonian is time independent. That is the way we have assumed. Do not think that Hamiltonian is going to be always time independent. There are ways to solve it in a different way, but so far we will use variable separation method to solve TDSE, and we will get a very simplified expression for the wave function very soon. What we are assuming that Hamiltonian is time independent, and because it is time independent, I will be able to take out time dependent part out of this Hamiltonian operator, and it is acting only on the space dependent wave function. Here, because it is a partial derivative with respect to t, I will be also able to take out space dependent part, and we can keep time dependent part as it is. So, I get finally this equation. Little bit rearrangement is needed. If I do that, then what I get is equals so what I get is that I have managed to reconfigure TDSE such a way that the left hand side of this equation is only time dependent and right hand side of this equation is only space dependent. And time and space, they are independent variables in TDSE. So, in order to have this relation, to hold this relation, all we need to consider is that this is going to be always constant. Two different variables cannot be equal, it has to be constant, and constant can be taken anything. For convenience we have taken E, because later we will find out that E, this constant, will be expressing the energy of that particle. That is why, because we knew that, that is why we are considering, otherwise you can take any constant. So, this is actually a constant. And once we take this constant, we will be able to separate these two variables, and we get one equation like this, that is called time independent Schrodinger equation. Another one we get is time dependent part, this part. So, this part comes here and this part comes here, time independent Schrodinger equation. This time independent Schrodinger equation, H psi equals E psi, here there is no time dependent part. This equation is an important equation, it is called eigenvalue equation. And this E is called eigenvalue, and psi x is called eigenstate, or eigenfunction. So, there are two equations we get from this variable separation method under these assumptions. There are two assumptions we have taken. Now, TDSE is a well known time independent Schrodinger equation, but the time dependent part, if I consider now, we will be able to integrate that time dependent part, and we will do that integration here. When I integrate it, I will be able to write down this equation as equals E dt, and I integrate it from 0 to t. When 0 to t I am integrating, I get psi 0 and psi t. This is the integration, and this gives me natural log of psi t which is nothing but Et or I h cut ln psi t minus ln psi 0 equals Et or I h cut ln psi t by psi 0 equals Et, or we can write down psi t equals psi 0 e to the power minus I Et by h cut. And so we get this equation. We know that total wave function has to be expressed as a product of this. So, finally, I will be able to express psi xt as psi x, then psi 0 e to the power minus I Et by h cut. That is the way we can express. Now, the psi naught, psi 0 is just a multiplicative factor, and in the end always we have to normalize the wave function. The wave function must satisfy this normalization condition all the time. This is called normalization condition, and wave function has to satisfy this condition all the time, because if a wave function is not satisfying normalization condition, it means that we have failed to give the statistical interpretation, and that's the only interpretation we have for the meaning of the quantum particle. So if statistical interpretation fails, then there is no meaning of quantum mechanics anymore. So in order to have that meaningful statistical interpretation of the wave function in quantum mechanics, the wave function at every time, for any time, it has to be normalized. So in the end we have to normalize the wave function, and any multiplicative factor can be included in the normalization condition. So what we can do is that instead of taking this multiplicative factor, we can generalize the solution, and we can say that this is what we have, the solution to TDSE under variable separation method, which means that I have assumptions, these two assumptions. So I have been able to separate space dependent function and a time dependent part. This time dependent part behaves like a time dependent phase factor. What does it mean by phase? We will discuss very soon. Phase is very difficult to understand. Phase is a physical quantity which is very difficult to understand, but we will spend some time on understanding this phase. In general, when we talk about the general solution TDSE, TISE, this TISE, when we solve this TISE, if we recall that one dimensional box for particle in one dimensional box, we have solved it, and when we have solved it, we have seen that we are not finding one solution. We said we get a set of solutions, and this wave function is given by psi n x, if we can recall. So TISE generally gives a set of solutions which are physically meaningful solution to the equation and to the TISE equation, and this set of solution actually represents possible states, stationary states of the particle. Particle can stay here, particle can stay here, particles can stay here, all possible states, but their energies are different. So each particle, depending on where they stay, the energies can be different. So this way energies increasing, and this kind of states are actually called the spectrum of the quantum system. So each solution is represented by psi n x, and that is called stationary state wave function. And n represents the quantum state, which means nth state, energy state. In chemistry, often we use this kind of energy states to express the spectrum of the atom and molecules using this stationary state, often from TISE, time independence Schrodinger equation. And so because time independence Schrodinger equation gives a number of states, we can final solution to TDSE can also be denoted with respect to its own state. So if the particle is staying at nth state, then its wave function, its time dependent wave function is given by this equation, where, as I have told you, this is the stationary state where the particle is. Let us say particle is in this state, that is why I have taken psi n, this is psi n, and its associated energy En. En is the associated energy of the particle. But if we look at this time dependent part is nothing but, it looks like a complex number denoted by I theta. A complex number can have different notation. I can have algebraic notation of complex number. Algebraic notation is A plus I B. That is the way we express. I is the complex number. And geometric notations, the same number, same physical quantity can be expressed in terms of this polar coordinate e to the power I theta. So, this is a geometric representation, geometric notation of the complex number. And this notation, this complex number shows that this is the time dependent phase factor. So, time dependent phase factor in the total wave function comes as a complex quantity, and the complex quantity is basically representing the geometric notation of a complex number. What is the meaning of this phase we will discuss, because phase has a very important effect. Phase is a physical quantity which we will discuss very soon, and it carries important information when two wave functions are compared, when two wave functions are interacting. At that time phase becomes an important issue. Otherwise phase will not be an issue. That will be demonstrated in the next slide. So, if we look at total wave function, the total wave function for a particular state is expressed by its space dependent part, and time dependent part comes into the picture as a phase, the complex temporal phase of the wave function. So, this is the if the particle is staying at the nth stationary state. So, we will distinguish two different states right now, stationary states and superposition state. What we see that wave function is time dependent, and if wave function is time dependent, this is a complex phase. If I try to think about real part, it is going to be cos Ent by h cut, some kind of a function of cos, and cos function is becoming 0, -1, +1, all these values it will take depending on what time it is. So, this wave function, if we look at this wave function for an example, at a particular time the wave function may look like this, next time the wave function may look like this, again the wave function may look like this. So, if we look at the wave function, it is continuously changing as a function of time. Changing what? Changing its phase. Changing its phase. Phase is some kind of color, one can say. So, some kind of sign. So, let us say if it is above this bar, I get positive, if it is below it is negative, if it is above is positive, some kind of like this, phase is changing. But as I mentioned before, that in the wave function is not something which we can directly observe through experiment. Can I observe it? No, it is not possible. only thing what I can observe is its density. What would be the density of this wave function? Like this. This is psi xt, this is psi n xt. So, experimentally relevant quantity density always be like this. It will be always like this. Why it will be always like this? It is because density is nothing but psi n star psi n xt, which is psi n star x e to the power I complex conjugate of that quantity multiplied by psi x e to the power minus I ent by h cut. We see that the moment we take the complex conjugate and multiply with its own, these two factors goes out. Phase factor will go out. Finally, what I get is a time independent, although I started with time dependent wave function, in the end it is giving me time independent physical quantity. So, density for a pure for a stationary state, and that is why this state is called stationary state. I have not discussed superposition state yet. I am discussing stationary state, and a state of the particle described by this equation is called stationary state because its density is not changing as a function of time. Its wave function is changing, as we can see, wave function is changing, it is changing its phase all the time, but its density is not changing as a function of time. And if the density is not changing as a function of time, experimental observables, any experiment I perform, I will not be able to see any change in the particle. So, there is no way I can see that change in the particle because I cannot observe the wave function. So, I repeat, I have a quantum particle mass m represented by staying in the stationary state psi n. Its wave function is time dependent, it is changing the phase all the time as a function of time, it is changing the phase, but there is no way I can see any change in the particle will look stationary. Because it looks stationary, this state represented by this wave function is called stationary state. We will move to superposition state now. Superposition state, what does it mean by superposition state? If we want to describe motion of a quantum particle, we have to describe the motion of the quantum particle not by the particular solution. So, we have expressed that particle is staying in this state if the particle is staying in this state, it is a stationary state. Its density does not change as a function of time. In order to observe a change in probability density, the particle has to be in a superposition state, and superposition state, what does it mean? I will be expressing this state of the particle, the wave function will be expressed as psi 1 h cut plus a2 psi 2 e to the minus I e to t by h cut. A linear combination of two stationary states I have to add. At least two stationary states need to be added to express the state of the particle. So, let us say I had a particle and these are the stationary states I had. Somehow I have managed, if the particle is staying only in this state, then density will never change as a function of time. But if I somehow manage to prepare a state where these two states are excited simultaneously, or in other words, there is a possibility the particle will be staying here and also particle will be staying here, single particle, but there is a possibility that particle will be staying in both states. That is called superposition state, and the whole quantum dynamics, basics of quantum dynamics depends on this superposition state. We have to create superposition state to observe temporal change in the particle density, the probability density, and that we can express very easily by taking only two equations, two states. We are linearly combining these two states. If we linearly combine these two states, then what is the probability density we get? We can see very easily that finally I get individual contributions plus both are time independent, plus there is a cross term which will come, psi 1 x psi 2 star x e to the power minus I e1 minus e2 t by h cut plus its complex conjugate. Often we write down complex conjugate as C dot C. In this class, in the ultrafast optics and spectroscopy, which I teach in NPTEL, in that course also you must have noticed that this complex conjugate comes into the picture, because whenever we use some complex number, its associated complex conjugate, we don't write it directly, but we just mention that there is a complex conjugate part. So, what we see here is that if I have e to the power I theta plus its complex conjugate e to the power minus I theta, I get 2 cos theta, we get the real part. So, these two together will give me the real part, which is going to be cos delta E t by h cut, and this is time dependent. So, density becomes time dependent. In this expression, the first term originates from the pure psi 1 state, second term comes from psi 2 states, and the third one develops an interference between two stationary states. The interference term is a result of having a superposition of the eigenstates with different energies, and this is called wave packet. The moment I create the superposition state, this wave function is called wave packet, and I need a wave packet to observe quantum dynamics. Anything I observe in the density change, temporal change in density, for that I need the wave packet, which means that the particle has to be in a superposition state. How do we create a superposition state? Simply by linearly combining two states with its characteristic phase factor. Characteristic phase factor should be also added together. Okay. The wave packet, which originates from a superposition of stationary states having different energies, is required in order to have a time dependence in probability density and in other experimental observables such as average position, average momentum of the particle. So, superposition state is very important. What we will do, we will just quickly give a metaphor. This kind of examples are not directly related, but we get to understand the meaning of stationary and superposition states in quantum mechanics. We all know that an octopus can change skin color to adapt its local environment, so that we cannot recognize it and that's the kind of a nature has given protecting ability to the species octopus. Now let's assume that the octopus is staying localized in this space between x1 to x2, and octopus is changing the color. That's exactly octopus is doing. It's not moving, it's staying at the same place but changing the color periodically. Let's say changing color periodically is represented by this phase factor. Phase factor, this is an oscillatory factor. This is a complex representation of an oscillatory part, which is nothing but a cos theta or cos kind of an function in a real sense. So when I say stationary state, it means that octopus is changing the color being in the same position between x1 to x2. Here also you see it's staying in the same position, and that's called stationary state. Wave function is changing color, but the total density is not moving. The octopus itself is not moving. But if I see octopus is moving now from position between x1 to x2 to x2 to x3 position, it's moving, it means that it is in the superposition state, and that's why we see the movement of the octopus body. So stationary state, it is stationary not because the wave function is time independent, but because its density is time independent, probability density is time independent. Something is superposition state, which is created by a wave packet, and a wave packet must be created to the wave packet is created through the superposition state, and a superposition state is absolutely needed to observe the quantum dynamics, to observe a change in the overall density. We will stop here and we will continue this module in the next session.